Good morning, everyone, and thank you for being here. My name is Alfie Yohannes, and together with my colleagues Winu, Suregar, Sanjaya, and Avrianto, I'm delighted to present our work at this 10th International Conference on Applying New Technology in Green Buildings. Our talk is about the carbon footprint of relational and hybrid object-relational storage for image-based time series workloads. In short, we ask a very practical question about green computing. When a smart building constantly stores camera images over time, which way of keeping those images is actually kinder to the planet? Let's dive in. Here's the path we'll take together. We'll start with the motivation, explaining why this question matters and what problem we're trying to solve. Then we'll walk through our approach and experimental setup so you can see exactly how the comparison was made. After that, we'll look at the results, both performance and carbon, and finally we'll close with a discussion and our conclusions. Think of it as a journey from why to how to what we found to what it means for you. Let's begin with the motivation behind this study. Imagine a modern smart building full of Internet of Things cameras, each snapping images stamped with the exact time they were taken. That data tier never sleeps. It runs 24 hours a day, 7 days a week, which means its energy consumption is operational carbon that accumulates relentlessly, month after month. Now, there are two very common ways to store one of these images in a PostgreSQL or TimescaleDB system. The first, which we'll call PG, keeps the image inline, directly inside a BYTEA column, and PostgreSQL quietly moves the large binary aside using a mechanism called toast, the oversized attribute storage technique. The second, which we'll call PM, externalizes the image to MinIO object storage and leaves only the lightweight metadata plus a key inside the database. Here's the gap we noticed. Most time series benchmarks use tiny numeric payloads, like a temperature reading, and almost none of them report energy at all. So our research question is deliberately concrete. What are the performance and carbon trade-offs of inline PG versus externalized PM storage? And how does that change as the image resolution grows? Put simply, is it greener to keep the picture inside the database or to ship it out to object storage? And under what conditions does the answer flip? With the motivation clear, let's look at how we actually set up the experiment. Here are the two architectures side by side, and the key idea is that they're deliberately almost identical. On the left, the pure PostgreSQL approach stores one row of metadata and then places the image inline in a BYTEA column, so everything lives in a single place. On the right, the hybrid approach still stores metadata plus a key in PostgreSQL, but the actual image object is pushed out to MinIO and retrieved over HTTP. The crucial point is that the data and the queries are the same in both. The only thing that differs is where the image physically lives. To make the comparison fair, we ran an identical workload on both, 7 image resolutions spanning from 360p all the way up to 5K, using JPEG images at quality 90, whose sizes range from about 90 kilobytes to just over 5 megabytes. We inserted 2,000 rows in batches of 50, and we repeated the whole insert process 5 times to get stable numbers. For reading, we tested the most demanding realistic case, a latest payload point read, fetching the newest image. And notice the asymmetry this creates. The hybrid PM path pays an extra driver round trip because it has to write each object to MinIO with an HTTP put and later fetch it back with a GET, whereas the inline path stays within a single database boundary. Now, let's make sure the measurement itself is trustworthy. Everything ran on a single host, an Intel Core i9-11900H with 31 gigabytes of RAM and a fast 1.9 terabyte NVMe solid-state drive. So both architectures faced exactly the same hardware under exactly the same conditions. To measure energy, we didn't guess. We read Intel's RAPL counters, the running average power limit, which report the actual energy drawn by the CPU and memory, and we did this through the CodeCarbon library. To turn energy into carbon, We used the Indonesian grid factor of roughly 0.676 kilograms of CO2, equivalent per kilowatt hour, which reflects where such a system might realistically run. On the right, you can see the full software stack we pinned down. Ubuntu 24.04, Docker with Compose, PostgreSQL 15 with TimescaleDB, MinIO, Python 3.14, and CodeCarbon 3.2.6. One caveat worth naming. The per-profile carbon uses a constant power rate estimate, but the whole phase totals are directly measured, so our headline numbers rest on real hardware-level energy readings. Now for the part everyone's been waiting for, the results. Let's start with raw performance, and this table tells a story of crossovers rather than a single winner. Look at insert throughput, measured in rows per second. At the small end, inline PG is dramatically faster. At 360p, it pushes over 730 rows per second against the hybrid's 100, and it keeps its lead all the way up through 1440p. But watch what happens at the top. At 4K and 5K, the roles reverse, and the hybrid PM actually inserts faster, 28.5 versus 23 rows per second at 4K, for instance. The point read column shows a similar flip. For the tiniest images, PG reads faster, but from 720p onward, the hybrid wins, and by 5K, it's reading roughly 8 times faster than the inline approach. There's one column where PM wins across the board, and that's storage amplification. The hybrid keeps storage essentially at 1.00 times the raw data, while inline PG carries a few percent of overhead. So the headline is that neither approach dominates everywhere. The best choice depends on how big your images are. This chart makes the insert story visual, and the shape is striking. The blue line, inline PG, starts sky-high at 360p and then plunges steeply as resolution climbs, because writing ever larger binaries through the database becomes progressively more expensive. The green line, the hybrid MinIO approach, is almost flat and comparatively low. It doesn't start fast, but it barely degrades. The two dotted horizontal lines mark practical frame rate budgets of 30 and 60 frames per second, giving you a sense of what real-time ingestion would demand. The key moment is where the blue and green lines cross, right around 1440p to 4K. Below that crossover, inline is the clear winner, up to about 8 times faster at 360p. Above it, the hybrid quietly takes the lead. The lesson is that a steep line always eventually falls below a flat one. Reading latency tells the mirror image of the same tale, and here lower is better. The blue inline curve stays low and comfortable at the small resolutions, but then curves sharply upward, climbing to about 27 milliseconds at 5K as PostgreSQL struggles to serve big binaries out of toast storage. The green hybrid curve, by contrast, stays almost flat and low the entire way because MinIO streams the object directly. The two horizontal budget lines show what a 30 frames per second and a 60 frames per second application can tolerate, 33 and 16.7 milliseconds respectively. Inline PG is faster only at the very smallest sizes, 360p and 480p. From 720p onward, MinIO's direct streaming wins, and by 5K, it's roughly 8 times quicker. So if your workload leans on reading large images, externalizing the payload keeps you comfortably inside your frame budget. Now we arrive at the heart of a green computing talk, the carbon numbers. This table breaks everything down per resolution, from benchmark duration in seconds through energy in microwatt hours split into CPU and RAM, all the way to emissions in milligrams of CO2 equivalent. And you can see the same crossover we've been tracking, now expressed in carbon. At the smaller resolutions, the inline PG values in the emissions column are lower and greener. At 360p, it emits 148 milligrams against the hybrid 662. But from 1440p upward, the balance tips, and at 4K and 5K, the hybrid becomes the greener option, emitting 2,376 milligrams versus PG's 4,826 at 4K. When you sum the whole phase across everything, the hybrid emits 14,483 milligrams of CO2, equivalent against inline's 19,825, which is a 26.9% reduction overall. The per profile crossover sits right at 1440p, where green becomes the greener choice. This chart decomposes where that carbon actually comes from, separating the insert cost from the point read cost. Notice the hybrid's disadvantage at small profiles. It pays a fixed HTTP put cost for every object it stores, so even for tiny images there's a baseline overhead that makes it emit more. But as resolution grows, that fixed cost becomes negligible compared to the savings, and from 1440p upward the hybrid pulls decisively ahead. By 4K and 5K, it's roughly having the carbon of the inline approach. The takeaway is that the hybrid's overhead is a constant tax that pays off handsomely once the payloads are large enough to dwarf it. This final results chart ties the whole story together by connecting energy to time. It overlays the CPU and RAM energy breakdown with a benchmark duration as dashed lines, and the pattern is beautifully consistent. The carbon crossover tracks the end-to-end time crossover almost exactly. In other words, the reason externalizing the payload saves carbon at high resolution is not mysterious. It's simply that shipping the image out to MinIO cuts the CPU and RAM energy that PostgreSQL would otherwise burn shoving huge binaries through its own machinery. Energy, time, and carbon all cross over at the same place, which gives us real confidence that the effect is genuine and mechanistic, not a measurement artifact. With the evidence laid out, let's step back and discuss what it all means and draw our conclusions. So why do these crossovers happen at all? The mechanism is straightforward once you see it. Inline PG wins on small writes because its batched inserts avoid a per-object network request, whereas the hybrid must pay a fixed MinIO put for every single image. But the hybrid wins on large payloads because PostgreSQL still logs those big BYTEA values through its write-ahead log, doubling the work, while MinIO simply streams the object without that overhead. And on storage, the hybrid stays at essentially 1.00 times against inline's 1.04. Translating this into practical guidance, for ingest-heavy workloads in the 360p to 1080p range, choose inline PG, which writes 2 to 8 times faster. In a mixed 1440p zone, it genuinely depends, but the hybrid cuts reads about 3.5 times and lowers carbon. For read-heavy 4K and 5K workloads, choose the hybrid, which reads 6 to 8 times faster and roughly halves the carbon. And if operational simplicity matters most, remember that inline PG keeps everything within one transactional boundary. The honest message is that these are crossover points, not a universal winner. Let me bring it all together. Our research question has a clear answer. Across the whole phase, the hybrid emits 14,483 milligrams of CO2, equivalent versus inline's 19,825, a 26.9% reduction. The crossovers are consistent. Inline writes faster up to 1440p, while the hybrid reads faster from 720p and is greener from 1440p onward. The hybrid also holds storage at about 1:1 and scales its write-ahead log with just the metadata rather than the payload. We're candid about the threats to validity. This is a single host. The per-profile carbon uses a constant power estimate, and we tested 2,000 rows. For future work, we'd like to explore multiple nodes and higher concurrency, and add PostgreSQL large objects as a third architecture. But the practical rule of thumb is simple: inline for small ingest and externalized object storage for large, read-heavy, carbon-sensitive tiers. That brings me to the end. Thank you very much for your attention, and I'd be very happy to take your questions and hear your thoughts.